Right, so hello and welcome to this second experiment in glider electronics. Last time what we did is we set up a glider electrical harness and showed that if we put a really strong signal down a pair of wires, we could get it to cross-talk into a second pair of wires and swamp out the really sensitive signal we had flowing in those. Now, it's important to realise that what we showed in the first experiment was just a single type of electrical interference that you can get in a glider harness. The intention of this series of experiments is kind of step through the different types, but electrical crosstalk is a nice sort of pure and simple one for a first demonstration. So today what we intend to do is take exactly the same experimental setup and just play around with a few things and see whether we can make the electrical crosstalk better or not. Standard disclaimer, I'm not a glider inspector, so therefore this is just an experiment where we're seeing what the results are. If you use anything from this video, then it's your responsibility to make sure it's right. I accept no liability. So, let's just run through quickly the experimental setup we had from last time. First of all, we've got a standard glider dynamic microphone, makes a very weak signal, goes down this bit of shielded cable here, and we put it into this connector block. We've then got a couple of really gash horrible cables, which is our sort of test area. This is where we're getting the electrical coupling across to. So we run down those cables into another connector block and then plug into an actual radio so that we have the right kind of input there. So we're not just making the experiment up. This really is a signal going from a microphone to a radio. Now, we then put this oscilloscope probe in after the input amplifier on the radio so that we can see exactly what the radio is seeing. So on the oscilloscope probe that we're recording here, I can put the scope probe up, and if I talk into the microphone, you can see on the scope probe that we get a trace coming out as you'd expect from a sort of sound wave of a voice. Okay, so that's our sensitive signal. It's about sort of 10 millivolts in size, so that's a really weak sensitive signal. We're then attacking it with the second signal, which is this one here. And here we're simulating a GPS talking to a moving map, which is a really strong, in gliders generally, a really strong RS-232 signal. Now, the key about these signals is, and we're simulating it here with this computer just off the screen here has a serial port on it and is going to this plug here. So it's a perfectly good simulation of the GPS. The moving map is simulated just with a resistor because that's a perfectly good simulation of the moving map. Now, down one of these wires we get a strong square wave going down it, okay? And it goes to the moving map. These are the ones and zeros of the lat long. Goes to the moving map, through the moving map, and returns down the second wire here, which is the ground wire. Now, reiterating from the first lecture, signals are always pairs of wires. When you put a current down one wire, it's got to come back to where it came from at some point. So all the way through these sort of experiments on electrical noise, we're going to be talking about signals as a pair of wires and a current flowing around them. Now, because there's a current flowing around these wires like this, and because this is essentially an aerial, this produces an electromagnetic field which couples into this other aerial here and generates a voltage/current in these wires that swamps out the other signal. So if we have a look at the scope, and if I'm just sort of talking on this, you can see my voice. But if I turn on this RS-232 signal, what you'll see is on this, this is the RS-232 signal at the top here. You'll see this become an actual sort of data signal, and you'll see noise suddenly appear on the microphone signal. So if I turn on the data, You can see the data's suddenly created there, and we've got a much thicker blob of noise on this microphone trace. If I just stop the data again, which will stop in just a second. So there we go, the data just stopped there, and we're now down to a much lower level of noise. So even with the wires sort of 10 centimeters apart, we're getting a reasonable amount of cross-coupling. If I turn the data back on, you can see the noise on the microphone signal jumps back up again. Okay. There's one more thing I need to say that we didn't cover last week about the electrical setup here. If I just put on the screen now how the microphone is wired up to the radio. If we start with the microphone, it has two wires coming out of it, and those go across to the radio. And the radio has two input pins. One of them is a ground, so we connect one of the microphone wires to ground, and that wire is then grounded. The other wire is the input to the input amplifier on the radio. So that's where it's reading the signal from. Now, because this radio has decided to ground one of the input wires from the microphone, this signal is therefore what's called an unbalanced signal. Any signal pair that has a ground in it is called an unbalanced signal. There's an entirely different category of signals called balanced signals. And so a more modern radio than this might well wire the microphone up as shown on the screen now. So the microphone has the two cables coming out of it, and they go into two inputs of the radio that are just called high and low, or A and B, or something like that. Now, there's no ground there, okay? Both of those inputs are read as signals by the radio. Now that is called a balanced signal, and balanced signals behave a bit differently to unbalanced signals. Balanced signals are explicitly designed to be a bit more tolerant at not picking up noise, okay? So I just want to state that there's a difference between unbalanced signals, e.g. signals with a ground, and balanced signals, which are slightly better at rejecting noise. So the whole of the experiment today is done with unbalanced signals, and in an entirely different experiment I'm going to deal with balanced signals. The reason why this older radio is not using a balanced signal is simply because of board real estate on the top here. It really doesn't look like there's enough space back in when it was built to put enough chips on to be able to process a balanced signal when it goes into the radio. Okay, so now we're going to do an experiment. We're going to change stuff up. We're going to see what changes. So the first thing we've got to do is find out how much experimental noise there is in the system. So literally what I'm going to do is just wire this microphone directly up to this radio and see what the noise level is. So I'll go into time-lapse mode and do that. Okay, and so we're back. Microphone is now wired directly to the radio, so we've got no wires here. We've removed as many wires as possible. We can find out how much electrical noise we're just getting in the experimental setup, and then we can subtract that from all the results that we collect during this experiment. I've got to stop the microphone hearing me, so I've got a box down here with a big duvet in, and I'm just going to push the microphone into the duvet so that it can't hear me and so my voice doesn't corrupt these results. So now you can see the microphone signal has gone flat, it can't hear me anymore. But we have a level of electrical noise still here, which is just the experimental electrical noise, and the scope is measuring the size of that down on this number at the bottom of the screen here. So if I run a single shot measurement of 2 seconds long, we can see that it's measured this green signal as a 4.4 millivolt signal. That's what the radio is currently hearing from the microphone. And we've still got the RS-232 spewing out electromagnetic noise. So any pickup in these wires here is measured in that 4.4 millivolts. Okay, now what I've done is I've run this experiment 3 times prior to filming this, and I've taken averages of all the results. So for this experimental noise number, what I got is 5.2 millivolts. So it's very close to this 4.4 we've got on the screen here. So if we start building up a table of results on the screen now, you can see that we've got, between the GPS and the moving map, we've got some straight wires. Between the mic and the mic is directly wired to the radio. We've got a raw noise voltage of 5.2 millivolts, that's the average of the 3 experiments. And notes on the side, this is the experimental noise measurement. Okay, so we've got the experimental noise, we'll subtract that off everything. Now what we've got to do is go and try and create the worst case scenario of coupling between this RS-232 signal and this microphone signal. So I'm just going to rewire all this again, back in a sec. Right, and we're back. So now we've got to create the worst case scenario and measure that. And I've been saying that this is a loop of current with a signal flowing down one wire and back down the ground wire and radiating electromagnetic energy out of this aerial. And this is another aerial that picks it up. So I've messed around with these wires for a while, and the worst case that I've found so far, if I'm bundling all these wires together in a tight bundle, like you might have in an aircraft harness, is if basically I'm overlapping the 2 loops. Okay, so the one aerial is coupling well into the other aerial. And if what I do is I lay the ground wire of the RS-232 and then take the ground wire of the microphone and put it next to it, and then take the signal wire of the RS-232 and then the signal wire of the microphone. If I push all those together, so I'm keeping them all flat on the table, and I push them all together like this and lay them out carefully. So in this, we've got ground RS-232, ground microphone, signal RS-232, signal microphone. So the 2 loops are overlapping each other. And if I carefully lay them out on the desk like this, and I'll go into time-lapse mode again and just carefully lay them out. So there we go, the 2 loops are carefully laid out on the desk with the 2 loops intersecting with each other. So hopefully we should get a good coupling between the 2 signals. So if we run a single shot here on the oscilloscope, you can see the noise on the microphone line just jumped up. And here we're measuring 33.8 millivolts. Now, the average that I got out of all the test runs was 35.7 millivolts. And if I just put that on the slide on the screen, so the experimental noise was 5.2 millivolts with the worst case overlapping wires. We got 35.7 millivolts, subtract out the experimental noise, we get 30.5 millivolts. And we're going to call this the worst case and call this 100% noise. Okay, so everything we're now going to compare to this case. So what's the next case we're going to try? If I take all of these bits of tape off here, I'm going to do something very minor. You might be thinking I'm about to swap these out for shielded cable or something like that, but I'm not. What I'm going to do is now, instead of having, basically we did have them with ground RS-232, signal RS-232, then we put the ground of the microphone in the middle. Okay. All I'm going to do is move this ground the other side of the signal line. So we've now got RS-232 ground, RS-232 signal, microphone ground, microphone signal. And again, I'm going to keep them all flat on the desk. and I'm just going to bunch them up so they're all lay flat on the desk. I'll just go into time lapse again, just stick all the bits of sticky tape on. Right, okay, so literally all we've done is untangled the two loops, okay? And literally we've just therefore moved one wire 2 millimeters this way and another wire 2 millimeters the other way. So we've moved two wires by 2 millimeters. Now, I want you to have a number in your head. How much do you think this is going to reduce the noise? Compared to the situation we just had where the two loops were intersecting and coupling, we've now taken the two loops apart and they're not coupling. Do you think this is going to have a 10% noise reduction, a 20% noise reduction, even a 30% noise reduction? I mean, how much do you think this noise is going to reduce? And I want you to get a figure in your head, okay? Right. So let's run the single shot and see how much the noise goes to. So this is the noise when the two loops were coupled. We run a single shot. Pretty serious reduction that you probably weren't expecting. If we run the numbers on this one's saying 9.2 millivolts. The average from the test runs was 10.4 millivolts, which means if we subtract out the experimental noise, that was 5.2 millivolts. So this is now 17% of the noise we had in the worst case. So we've had over an 80% noise reduction, literally by moving two wires 2 millimeters. Now this is sort of really important about noise reduction. Noise reduction is not just about shielding everything. It's about decoupling loops of current and things like that. And you can do, as you see from this experiment here, you can do that with really, really subtle changes. No shield involved. And I've moved two wires 2 millimeters, and I've got an 80% noise reduction in the noise pickup in the microphone. So we'll see more through these experiments how subtle little changes can make all the difference. And it's not all about shielding. Right. Now, this isn't necessarily particularly useful to you if you're wiring up a bunch of wires in a glider harness, because if you've got them just in a bundle with some cable ties, how do you stop one wire sort of getting in between two other wires and coupling? It can also explain if you have got a bundle that, let's say, goes through the hinge in your canopy, why just opening and closing your canopy can move the wires around, change the coupling between the wires, and you can get a completely different level of noise in your glider. So on the surface of it, this is not very helpful. If you're an electrical engineer and you're designing something that has a bit of ribbon cable, then it's very useful, because what it says to you is in a ribbon cable, you put ground signal, ground signal, ground signal up the ribbon cable. If you stick two signals together, without their associated grounds separating them, you're going to get a lot of noise in it. So that you're not going to use in a glider, but you'd use in a piece of electronics. Much more likely in a glider is this, for example, is a FLAM data and power cable. And this data cable that sort of looks like it has a phone connector on the end, sort of a standard telephone type connector. This, I believe, actually is a ribbon cable. It's a flat cable with the wires all carefully aligned. So in this, the designer of the piece of electronics at the end can carefully align all the signals so that you've got ground signal, ground signal, ground signal, etc. So these ribbon cables should really be doing this kind of thing and sort of laying stuff out. Okay, so that's not very practical if you actually have a bundle of wires in a harness. So we're going to have to talk about something a little more practical in terms of reducing noise. That's where something like a twisted pair cable comes in. So here we've literally just got two wires and the two cables are twisted together. And these are just twisted as much as the wire will take. Before it starts kinking, if I twist the two cables for any more, it'll get weird kinks in it. So what we're now going to do is replace the microphone cables with a twisted pair and see how this compares to the worst case scenario. Okay. Right, and we're back. So microphone's now a twisted pair. RS-232 is still a couple of wires. What we're going to do to try to make this worst case is stick the twisted pair in between the two wires of the RS-23 cable and pin it all down again. Now, a number of you have asked over the last couple of weeks to hear what this interference sounds like. I am going to do that, but I'm going to do it at the end. So we've now got this microphone twisted pair down the middle of the two untwisted RS-232 lines. Let's have a look at what this noise is like. So we can see it's jumped up a little bit from the case where we essentially had the sort of ribbon cable-like design. And we're getting 16.5 on the scope here. The average from the three experiments that I ran was 18.8. And that therefore means 13.6 millivolts once we've subtracted out the experimental noise. So the twisted pair on the microphone cable, that's got us down to 45% of the worst case noise. Okay, so it's not as good as the ribbon cable, but it's a respectable result. Let's twist the other pair. So we haven't twisted the RS-232 line. Let's twist that one and see what happens. Now, you might ask, what exactly is this twisted pair doing? How exactly are we causing a noise reduction? The first thing is just a mechanical one. We saw that with the straight wires, if we just move them from being or overlapping each other in their pairs, if we just move them apart, we suddenly got much better noise performance. By twisting them essentially mechanically, particularly if we've got two twisted pairs rather than one, mechanically these just can't overlap each other anymore. They're mechanically moved apart. So without having to use a ribbon cable, just using normal aircraft cable, we've therefore mechanically sort of separated the two loops. But there's a second thing going on here, which is here, this aerial from this RS-232 line is radiating out a nice uniform field. And if we put another pair of cables on top of it that are also flat, it's going to couple nice and uniform and nice and strongly. What this does is continuously twists the aerial around. You'll know from your TVs and radios that aerials can be quite directional. So this twists the aerial around. So if this is a transmitting line that's transmitting noise, we're scattering the radio or the electromagnetic interference off in different directions as we go along the cable. If we're twisting the receiver, we're twisting the direction that the cable is receiving from all the way along. So particularly, I mean, if we've got two of these cables like this, we're scattering the transmission and we're scattering the direction we're receiving. So we should get a much lower coupling between the two cables. Now, these should perform better in the balanced case. This, remember, is the unbalanced case. Balanced has some particular properties where a twisted pair should really come in its own. But we'll see that when we tackle balanced cables in another experiment. So this one should have a reasonable result, but it's not as good as twisted pair should be. Okay, I'll just swap out this cable. Okay, right, so now both the RS-232 and the microphone connection are twisted pair. Let's see what that difference that makes to the noise. So this is the noise from just the microphone being twisted pair and the RS-232 being straight wires. We run this, we can see it's dropped. So we're now down to 11 millivolts. If we put that on the table, 11 millivolts, subtract out the experimental noise, get 6.4 millivolts. So we're now down to 21% of the original worst case noise. So with twisted pair in their non-ideal situation, because this is an unbalanced circuit, not a balanced circuit, we basically got down to the same result as with the straight wires and in a ribbon cable, untangling the two loops. So we found a much more compatible method with sort of glider wiring of getting an 80% noise reduction, basically. But it's utterly critical with a twisted pair that you are twisting together the signal with its ground return. Or its associated current return if it's a more balanced signal where it doesn't exactly have a ground. If you're twisting together wires that aren't a signal pair, that aren't the two wires in a signal, all hell's going to break loose. Also, the other thing is all of these things we're doing probably don't matter at all if you don't wire the ends up correctly. Okay, if you don't follow the manual as to how you wire the ends up, no amount of shielding or twisting or anything like that is going to get rid of the noise, because if you wire the wrong pin to the wrong pin, you completely destroy what the electronics designer's trying to do in their electronics, and all hell can break loose. Okay, so we've got a method now of getting an 80% noise reduction with standard aircraft wiring. But that's only an 80% noise reduction. We've still got quite a reasonable amount of noise there. And for this weak microphone signal, that might not be enough. We'll see at the end when we listen to them. This is probably plenty for a digital signal. If you're trying to stop noise getting into another digital signal, then this kind of 80% noise reduction between two signals is probably fine for getting a strong digital signal to talk properly to another device. But for this sensitive microphone signal, we need more. So what we're going to do is swap out the microphone signal with a shielded cable and replace the RS-232 signal with straight cables again to give the shield its sort of worst case challenge. So I'll do that. Right, so we've now got the shielded microphone cable lay between the two straight RS-232 cables. Now, before we look at how much noise there is on this, it's important to note on this scope that this is the noise from the case where we have the two twisted pairs. This is quite a dense noise. It goes from top to bottom, and the scope is measuring that dense noise. If I now look at the noise on this shielded pair, the scope will measure a fairly similar thing. So it's measuring 7.2 millivolts. The two twisted pair case was 11 millivolts. But if we look at this signal, we can see here there's a dense noise in the middle, but then there's these tiny little spikes coming off the noise trace, which is what the scope's measuring. So if we do the measurements exactly as we've done the previous measurements, and we put this result on the graph, then this shielded cable only gets down to 14% of the worst case noise. But really, if we sort of ignore these little spikes, that shouldn't make much difference to the audio. The shielded cable is getting much more down to the sort of 5 millivolts of experimental noise that we were seeing at the start. So really this shielded cable has pretty much got rid of all of the noise from the signal, and we will definitely see that when we listen to them in a second. Okay, so what have we seen so far? We've seen that simply if we've got cables laid out, then going from the worst case of interlocking the two loops of signals, just moving the signals apart, moving the wires a couple of millimeters, we can get an 80% noise reduction. That's difficult to do with random wires in an electrical harness. So we've seen that if we twist the signal with its ground return, or the two halves of a balanced signal, we can get a similar 80% noise reduction as we could in a kind of a ribbon cable type structure. And we've also seen that a shielded cable gets us pretty much down to almost no noise. Now, to hear what the audio is like in each of these test configurations, I've recorded some test patterns on the microphone and recorded them on the scope. That allows me to take them across to a computer and play them. I've decided not to put those audio clips into this video because I don't want someone to be asleep on the sofa listening to it on headphones and me blast a load of static into their ears. So if you want to listen to the audio clips from each of these test configurations, then there's a video at this link here, which has an appropriately harsh health warning at the beginning of it, and that'll show you what the audio is like in each of these test configurations. So that's it for today. At the end, I'll put up the slide with all the test results again. Feel free to like or subscribe and get in contact with me. Your comments are most helpful, and I'll see you next time. Thank you very much.